How's it going? Vortex is something that is kind of mesmerizing. It's cool to see them. If you see them, I feel like tornadoes are like it's a vortex of sorts. It's like a vortex that touches ground. It starts in the air, I think usually. Um, I think whirlpools are like vortex phenomenon. And like eddies in a stream. I think there are kind of vortices, and I'm not really sure what they are, and that's what brings me here. This is a phenomenon in fluid dynamics. It's a region in a fluid which the flow revolves around an axis line. So I'm reading right here, which may be straight or curved. This is from, yeah, these are legit resources from, I don't know about this one, but this one might be good. I don't know, actually. Vortices form in stirred fluids and may be observed in smoke rings, whirlpools, the wake of a boat, winds surrounding a tropical cyclone, tornado, dust devil. So it's this like phenomenon in fluid dynamics. And fluids are, so sometimes when you think about a fluid, you might intuitively think of liquids, but gases are fluids, like or from a physics standpoint, fluids include gases as well. So it's gases and liquids. They both behave physically like fluids, which might be counterintuitive. But when you think about, the fact that you can have sort of a vortex of water and also of air in the form of like a tornado or something, then maybe it becomes more kind of understandable that that's the case. So vortices are a component of turbulent flow. And it's not only is that they are a component, they're a major component. So it's like the vortex is a major component of this thing called turbulent flow. Without getting into that, rabbit hole, I'm going to keep going. So the distribution of velocity, vorticity, which is in parentheses the curl of the flow velocity. Curl is this is a concept from vector calculus. So curl can also be called rotor, and it's a vector operator that describes the infinitesimal circulation of a vector field in three-dimensional Euclidean space. Okay, so vorticity is the curl of the flow velocity, as well as the concept of circulation, which are used to characterize vortices. In most vortices, the fluid flow velocity is greater next to its axis and decreases in inverse proportion from the distance of the axis. For example, this. So if this is our axis, there was no need to like go in this deep, but if this is the axis point from which everything is curling inwards, then that statement saying that the greatest speed will be observed as close as possible to that axis, and it will decrease in speed inversely as the inversely with the distance as we travel out. Okay, of that axis point. Okay, we're back. So, in the absence of external forces, viscous friction within the fluid tends to organize the flow in a collection of irrotational vortices, possibly superimposed. Okay, this is a large sentence that has 0 citations, which is something I don't like. So I'm not really sure about what to make of it. So there are different types of vortex. In theory, the speed, which is we mark as u. So u is like speed. Also velocity. Therefore, velocity is speed but with direction. So speed would just be a magnitude, just like 30 miles an hour. But the moment you're saying, okay, 30 miles an hour due east, or in some sort of direction on a Euclidean or on a Cartesian plane, then this is velocity. So it says the speed u, and therefore the vorticity. We skipped over vorticity. Let's go to vorticity really quick. So vorticity is a key concept in the dynamics of so vorticity is a key concept in the dynamics of vortices. It is the vorticity, or it's a vector. So vector has direction, right? Direction and magnitude. And it describes the local rotary motion at a point in the fluid, as would be perceived by observer that moves along with it. Conceptually, the vorticity could be observed by placing a tiny, rough ball at the point in question, free to move with the fluid, and observing how it rotates about its center. Awesome. That's super intuitive. So just putting a ball and then just seeing how it is rotated. The direction of vorticity is defined to be the direction of the axis of the imaginary ball according to the right-hand rule. Now we're getting into sort of the nitty-gritty. So let's see if we can understand. So direction of the vorticity vector is defined to be the direction of the axis. So the axis, we have the axis of rotation. So like going back to this picture of the tornado. So there's the axis. It's rotating. Where was I? Sorry. Yeah, it's defined as the axis of rotation of the imaginary ball, according to the right-hand rule. I think the right-hand rule is, you put your hand out. Let's see, the right-hand rule. So it's a convention in physics and mathematics. So yeah, of a rotating body. So if my thumb is pointed up, then my fingers are curling around. So that's the right-hand rule. So according to the right-hand rule, with its length, while its length is twice the ball's angular velocity, its length is, so angular velocity, so it's how quickly an object rotates around an axis of rotation around itself. So mathematically, vorticity is defined as the curl or rotational of the velocity field of the fluid, usually denoted by, I forget which, excuse me, I don't remember what Greek letter that is, but it's with a top hat, that little vector symbol, and it's expressed by the vector analysis formula, which is, so this is the nabla cross product with u velocity. So nabla is the operator. The nabla, I think that's the curl, and it's the local flow velocity. Interesting. So the local rotation measured by the vorticity must not be confused with angular velocity of that portion of the fluid with respect to the external environment and a fixed axis. In a vortex, in particular, may be opposed to the mean angular velocity vector of the fluid relative to the vortex's axis. I'm pausing this here because I'm getting a little bit A little bit tired and I'm losing focus.